Today we are listening to a talk by Boon Chian, who is a PhD student at Universiti Putra, Malaysia, and now Erasmus Plus in the Erasmus Plus project here in our group of cryptography and number theory of the Department of Mathematics at Polytechnic of Turin. So I see that we are already a good number, so I think we can start. Okay, so Boon Chian is talking about Coppersmith method solutions to modular polynomials. Thank you.
Yes, thank you, Simone, for the brief introduction. Buongiorno a tutti. So I am Boon Chian here, a PhD student from Universiti Putra, Malaysia, and I am now doing the Erasmus Plus Mobility Program in Politecnico di Torino. And I will be doing my second sharing session today. So about this Coppersmith method, the solutions to modular polynomials. Just to capture a bit, my supervisor from my home university is Associate Professor Dr. Muhammad Reza Kami Arifin, and my supervisor here in Polito will be Professor Dr. Bazanella Danilo. And I would prefer to use the term sharing session instead of giving a public seminar, because what I'm going to do later are based on my self-study and self-understanding. So this is the outline of my session. So the first part will focus on the Coppersmith method in univariate case. And if the time permits, then I will go to the sixth part, which is the solution to multivariate polynomials. And we shall see how the time managed later. And just before I start this session, I would like to put some disclaimer. And again, all the content presented in this session are solely based on my personal study and understanding. And certainly, I believe there are many theories and updates that I overlook and are not deeply familiar with. And if there is any facts or statements presented later are wrong or incorrect, please correct me so that I can understand and learn better too. And what motivates me to share this or to study this topic is first, Coppersmith method is actually a very popular method in cryptanalyzing the RSA crypto system. Now, from the RSA key equations to the small public or private exponents up to partial key exposure and etc., all this can be analyzed using Coppersmith method. So it's a popular. And also, it is one of the powerful methods to deal with the small integer solutions to both the integer and modular polynomials. And it involves lattices and also often applied in analyzing multivariate cryptography and lattice-based cryptography. So something could be useful when we want to study post-quantum cryptography also. And last but not least, this method is elegant, but a bit confusing for a beginner who are not familiar with it. That is me. So that's why I choose to study myself and try to go deeply with it. Now, before we move to the methods of Coppersmith, so some simple introduction. So those who are in the number theoretic fields should be familiar with modular polynomials and modular equations. So here in this case, I just denote the univariate function fx, okay, with the degree greater than 1. And now we are interested to find the roots to the modular equation such that fx congruent 0 modular n. Now, it is stated that if the factorization of the composite number n is known, then solving these modular equations is easy. Otherwise, it could be difficult. Now, the specific case is if this modular equation has small solutions, then we are not sure whether is it necessarily to be hard to solve it or not, or there's no certain answer. So Hastad in 1988 firstly addressed the similar problem of solving the monic polynomial, a modular polynomial, with the condition of x is strictly less than the minimum of n, and n composed by k distinct prime, which means n is a multi-prime composite number. Now, Hastad proved that if this condition satisfied, then the roots can be recovered in polynomial time. Now, about a decade later, Coppersmith devised another method to search the small roots in polynomial time with the condition this x0 is the solution and satisfy this second inequality. So these are the two brief timelines that I would like to address since I'm discussing sharing about Coppersmith. And the central problem now is, if we know there exists at least one root to the modular polynomial, and that root satisfies what Coppersmith proposed, the question is, how could we find them? Now, from the facts of this central problem, if we know that if the root is at most n power 1 over d, it is definitely less than n. Now, moreover, if the coefficient of the modular function is small enough, then there is a possibility that we have the root such that fx0 equals to 0 over integer. And in this case, then any numerical methods such as Newton's-Raphson method can be used to find such approximation. And then we check whether this approximated value is indeed the root to the modular polynomial or not. So if the coefficient I is small enough, then this method is applicable. But what if this coefficient AI are not small? Now, Coppersmith has an idea to deal with it. If the coefficient of the modular function is not small, then we can build another polynomial Gx from the original fx that still has the same root to the equation, but with smaller coefficients of AI. So in other words, from the original fx, we build Gx, but still retain the same solution. So this is what Coppersmith's idea is. And to illustrate this simple toy example we'll do, so let's say now we have this function fx, x squared plus 33x plus 215. Now we want to find the root x0 such that fx0 congruent 0 modular 3 to 3. So the solution is that we try to set another polynomial of Gx, which composed by 9 multiply fx, subtract to 3 to 3, multiply x plus 6. So this Gx is built from fx and the module composite number n. So this constructed Gx gives us the function with small coefficient, and we can even factorize this into two different factors. And notice that x minus 3, it's one of the factor which is an integer solution to Gx equals to 0, and also the solution to fx congruent 0 mod 3 to 3. So this simple toy example illustrates what Coppersmith tried to propose earlier. And after knowing the idea of Coppersmith and some of the brief introduction about the modular polynomial equations, then there are some important theorems and background that will be helpful in dealing with the Coppersmith method in section 4 later. So the first theorem is due to Hargrave-Graham, which says that given a polynomial of fx, and we can always associate a row vector in this form. And if the norm of this associated row vector satisfies this condition, n over square of d plus 1, then the root x0 gives fx0 equals to 0. Now, in this case, I am not going to discuss in detail about the proof, since my main objective here is to show possibly step-by-step how to apply this Coppersmith method. But later on, I will include the reference that I use in preparing my materials. So if you're interested to go further in understanding these theorems, yeah, you can do so. So this is the first theorem due to Hargrave-Graham. And second will be the definition of how to form the basis of the lattice. Now, suppose we have Gix, be the d plus 1 polynomials that has the root x0 modular n, then we can define a basis B that corresponds to this polynomial Gix together with fx for a lattice L as follows. Now, this definition is basically the fundamental pave that most people use in applying Coppersmith. Okay, personally, I sometimes find that this approach is although straightforward, but a little bit complicated, because sometimes the straightforward method does not output the solution as a wish, but sometimes it does. So this definition one itself, it's applicable in solving the Coppersmith, in solving the modular polynomial, but sometimes it does not do it straightforwardly. And in the second theorem, now suppose we are given the basis B as defined in the definition one, this lattice, okay, and Gx be the polynomial corresponds to the first factor in the LLL reduced basis for the lattice L. Now, if this integer x satisfies this condition, then any root x0 of fx mod n such that the x0 satisfies this integer less than x satisfy this Gx0 equals to 0 in integer over z. Now, I put a remark here. Sometimes the small root may be found even the root x0 does not satisfy this condition. And later on, there will be a few examples that I demonstrated to capture this remark number one. Okay, after having that two theorems and definitions, okay, then now we can move into the full Coppersmith method. Now, considering the theorem 2 just now, okay, which means that the success of finding the small root of the polynomial, the modular polynomial, is essentially this. Okay, so this is from the full Coppersmith method. Now, there are two strategies, okay, for us to increase or to enlarge the size of this integer x in this equation 3. So the first strategy is to increase the dimension of the basis, okay, by adding the rows to the lattice that contribute less than n to the determinant, that is the x shift in the polynomial. So this first strategy is basically very similar to the definition one. So if we notice carefully, except the last row, which comes from the original fx function, the remaining rows are basically just the x shift of the modular n. So this is what captured in the first strategy. Second, we can also increase the power of n on the right-hand side in this equation, in equality, okay, by using the power of fx. So since if fx not congruent n modular n, then f power k x not also congruent n modular n power k. Now, I try to highlight this part here because as a beginner, I noticed that this is not so obvious why the second strategy is in fact. So after performing some simple proof, now indeed, if x0 is the root of the modular function, then we can express this fx as x minus x0. This is the factor, okay, multiplied by px plus n qx. So px, qx here are just some other two polynomials of degree less than fx. Now, if we power both sides with k by the binomial expansion, then we have this last series of terms. And notice that all the terms here, except the last one, contains the factor of x minus x0. So substituting back, then the whole except the last term vanish. So this directly proves that. So if we have fx not congruent 0 mod n, then fx dot power k congruent 0 mod n power k as well. So once we understand how these two strategies work in full Coppersmith method, then we can look at the theorem proposed by Coppersmith, which says that let epsilon, okay, bounded by 0 and minimum 0.18 and 1 over d. So this condition comes from the proof later on. So if let fx be a monic polynomial of degree d, that with at least one small root x0 modular n, such that this condition is satisfied, then this x0 can be found in polynomial time. Now, for the case of the proof, I try to copy and paste from the original reference since there are certain things that they are well explained there, and I want to highlight and draw the reader's attention. So note that to avoid confusion, I try to change the m in this proof using n, the letter n, because this m will also be used in the later part of the slide, but represent another notations. So to avoid confusion, I try to use the modular for n to standardize this usage of the notation. So just treat all the m here as n. So the first thing that I want to draw the attention in this Coppersmith method is the first line, that let h greater than 1 be an integer that depends on the d and epsilon that will be determined later in the equation 19.3, which is in the subsequent slide. So the second point that I want to draw attention is this Gijx polynomial. Now, this polynomial is actually the one that should be used when we try to apply Coppersmith method in building the basis instead of following strictly from the definition one. This should be the original one that we refer to when applying the Coppersmith. So having these two main important points, then the next will be the 19.3, which corresponds to the first line. So this is the formula for h, which we are going to determine what value of h that is suitable for us to apply the Coppersmith method. And the last part will be in this almost the end of the proof, that is x is equal to d epsilon over d minus 1. And solving, since this is equivalent to this inequality, the solution of this x turns out to be bounded by 0 and 0.18. So this is how the condition in the theorem here is obtained. If epsilon tends to 0, then it will be 1 over d. So this is how the pair of 0.18 and 1 over d are obtained. So like I said, this proof is actually very elegant and very beautiful. If you go through one by one slowly, you will notice that, wow, this is wow, and how Coppersmith actually devised such good method in solving and in dealing these modular equations. Okay, and yeah, let's try to consider this example and also how we can solve these modular equations by applying what the highlighted points that I mentioned just now. So suppose now we have this large composite number of n, and we have this polynomial fx. Of course, they are all in a very large coefficient. Now we are interested to find the root x0, okay, such that x0 is at most 2 power 15. So this is the capital X that mentioned in the earlier slides. Okay, now from the proof of the theorem 3, if you still remember the two parts that are highlighted in for the x and the 0.18, that part. So using these two facts, so we have this next condition. So since d epsilon over d minus 1 is at most 0.18, taking the reciprocal, it becomes d minus 1 over d epsilon, at least 1 over 0.18. So, and that if we apply the h formula, which is also highlighted previously, and we can notice that h is at least 2.2. So since h must be an integer, so here h equals to 3 will be a suitable choice in applying this Coppersmith method. Now, having this h equals to 3, then we can start to construct the polynomial gx from fx. So this part is also highlighted in the previous proof. So I capture it again here. So we have this Gij, which is n power h minus 1 minus j, capital X power I, and the function fx power j. So with the condition I is in between 0 and d equals to 3, this is exclusive, and j is in between 0 and h equals to 3, exclusive. So substituting all this ij value, now we can build these 9 different functions. And arranging them accordingly, this actually forms a basis lattice B of dimension of 9, which is this. So it's actually a quite large, so to save space, I try to use A0, A1, A2 to denote the coefficient. So this should be x2 power 15, it's not 14 here, sorry. Now, once we have this basis lattice form, then we can start to execute the algorithm. So here I will just to demonstrate the algorithm here. So this is the first case of the dimension 9. So having the same, can you see the maple? So I should just, hold on. Now can you? Yes. Okay, now, so this is the problem that corresponds to the example 2 just now. So once we have formed, this is the matrix, the basis lattice. So once we have formed that, so with the x 2 to power 15, and we start to run it, and also the algorithm. So in the end, it turns out to be the root of the modular polynomial is to be 16384. Okay. So which corresponds to the solution here. And we can, of course, you can check again that it is indeed that gives the solution to the modular polynomial above. Now, so this is if we follow exactly how the Coppersmith method, okay, in determining the H and using the D and all the formulas that I highlighted in the proof. So this is how the complete formal solution to be. But notice that if I try to eliminate the last 2 rows and columns, so in other words, if I try to exclude the last 2 constructed Gx function, then I have a smaller basis of dimension 7. Okay. And again, if I try to use the same problem of dimension 7 with the same facts and run again, so smaller dimensions still output the same solution. Is this the one? Yes. So in the end, it still returns the same solution to the problem. So now this becomes interesting. So if we try to follow exactly how the Coppersmith method proposed, we get the same solution. Now, if we try to reduce the dimension by excluding certain function, certain constructed Gx function, we also apply the same we also obtain the same answer. So these are some of the self-interesting discovery that I found. So the one point is reducing the dimension, which I will talk about later. So the first thing that I would like to draw the attention is that sometimes if the value of x that I chose, okay, it's less than the value of the root, the method still works and you still possible to obtain the root of the modular polynomial. Just make sure it's not too small. Now, this is actually what captured in the remark 1 just now, which says that sometimes if the root does not satisfy certain condition, we still can find the root of the polynomial. So to capture this, I would use this dimension 9. So let's say now, instead of using 2 power 15, let's change to 2 power 12. Now, definitely, this value is smaller than the root that we obtained just now. However, if I try to run this program again, in the end, I will still obtain the same solution of the LLL from the LLL algorithm. So this becomes interesting because even though we try to violate or deviate a bit from the Coppersmith method, but still we obtain the same solution. So this is one of the interesting discovery. Second, the solution will occur at the first row after the LLL basis reduction. So in fact, with suitably chosen X, the solution will appear in every row most of the time of the LLL reduced matrix. Now, why this second point attracts my attention is that previously when I tried to discuss with some students, they inform and they share with me that most of the time when they try to perform Coppersmith method, their solution does not appear in the first row, instead somewhere in between. So this makes them have to check every line of the reduced basis in order to verify the answer. But after myself deeply study, I noticed that most of the time, the first row always gives you the answer regardless of how you manipulate this value x, as long as this x should not be too small. Okay, let's say if I try to make it into 2 power 10, which is definitely smaller. Oops. Okay, with 1 to 0, then this LLL, this Coppersmith method in the end will not return any solution at any point. As you can see, F10, F9, F8. So all the rows do not return the roots. So in fact, if we try to stick to the original value of x to power 15 and run once again. So let's check in a smaller version so that you can see it clearly. So this is the root found in the first row. This is the root found for the second row of the reduced basis. This is from the third, from the fourth, from the fifth, and so on. So like I mentioned just now, if you really choose the suitable x in your Coppersmith method, the first row guarantees the solution, but the other rows will also output the same solution. And last one is that sometimes in order for us to save time in considering how many or how large the dimension of the basis that we should form, it is helpful to consider the polynomial up to f squared. Okay, so this is what captured in this example 2. This example 2, where I try to eliminate the last 2 rows and columns, which means if I try to exclude these 2 functions, I can still obtain the root. So which means in this case, I only consider up to f squared in my construction of Gx. And I have tried to experiment it for quite a few examples. And indeed, most of the time, if you try to consider the polynomial up to f squared, it suffices for you to build a good basis and output the solutions, the root, and the root will always occur in the first row. But in some special cases, which I read from many RSA papers, even the original fx suffices to form the basis and output the solution. So this is why a Coppersmith method, although elegant, it's also known as a heuristic method. You have to perform some trials in order to verify whether it works to you efficiently or not. Or if it doesn't, then you might need to increase a dimension a bit and try again in order to search for the roots to the modular polynomial. So these are some of the self-discovery and self-studying what I obtained along this in this Coppersmith method. But of course, the application of the Coppersmith method, like I mentioned in the earlier slide, it is always used in cryptanalyzing RSA crypto systems. So such as the small public exponent, small private exponents, or even partial secret key exposure. Okay, and yeah, with partial knowledge of P, the prime P, we can factor the n equals to PQ, or it is also frequently used in cryptanalyzing the multi-prime RSA, P power RQ. And since, like I mentioned also in the earlier, it involves lattices, even learning with errors also uses a Coppersmith method to analyze the scheme. And the latest research trend is that some also apply the Coppersmith method in solving the hidden number problem. Now, this is the problem introduced by Bonnet in attempt to analyze the Diffie-Hellman key exchange in another perspective. It's also quite interesting and it's worth to go through if you are interested. Now, okay, so these are some of the first part. It deals with the univariate polynomial for the Coppersmith method. And yeah, of course, it's quite straightforward since we have only one single variable and it can be easily implemented. So like I also mentioned in the previous slide, even the original polynomial suffice to build a good basis and you can run it and obtain the root. And even if it does not work, then by a small modification, you can still proceed and obtain the root to this polynomials. Now the case is, what if we are interested to find the roots of multivariate polynomials? Now in this case, we have more variables. Besides x, we can include y. So if we have more than 2 variables in one polynomial, then how can we use the Coppersmith approach to find the roots? So this is actually in the number 6, and I have a little bit of time. Is it? So I can continue a bit. So if I can't finish it, then never mind, because this slide will also be available for you to download and have a copy. You can also have a look after that. Now, so in this multivariate case, I try to consider only the modular bivariate polynomial, because understanding this allows us to extend to triple and quadruple and so on. Now, the definition, it's still similar. Suppose we are given a function of 2 variables x and y, and we are interested to find at least one root x naught y naught that satisfies this condition. So if you look at this definition, it's basically just similar as in the univariate case. Now, of course, we can apply the strategy of Coppersmith, hoping to find 2 polynomials after the LLL basis reduction. Okay, 2 polynomials fx, f1, f2, such that they both gives the same zeros, okay, and they are algebraically independent. So, but finding this could be another problem later on. So, okay, applying the Coppersmith method, then we have this theorem. Okay, basically it's also captured what Coppersmith's approach. So let fxy be the ring polynomial of total degree d, and xyn are some natural numbers such that the product of xy is less than n power 1 over d minus epsilon. So this condition is also similar to the Coppersmith in univariate case. Now, then one can find the polynomials of f1 and f2, okay, such that the root for all roots in Z2, okay, fx naught y naught is congruent to 0 modular n, and this f1 and f2 are algebraically independent. Now, as the above theorem considers the case of the modular forms, the original references suggested reader to refer to Jutla and Nguyen and Stern's work for the proof. But personally, I consider the work done by Joachim and Mays because their heuristic strategy covers both in finding the modular and integer roots of multivariate polynomial by modifying the strategy accordingly. So in other words, although Jutla and Nguyen and Stern has their own proof and in their own way to solve this bivariate modular polynomial, Joachim and Mays also has their own method, but in this case, I try to consider the work done by Joachim and Mays. There are some reasons based on my personal choice. And of course, there are still many other strategies that have been proposed. For instance, Bonnet and Delphi also proposed their method in dealing with this problem. Blomer and May also has their own strategy. And why I choose to use Joachim May's method or approach is that their way of finding the roots of modular multivariate polynomial is easier to understand from the beginner point of view, because later on when we try to consider how they construct the polynomial Gx from fx, the approaches are basically similar to the Coppersmith case. So which is easier to deal with when we try to shift from univariate to multivariate. So let's have a small peek on this Joachim May's basic strategy. And so let epsilon be 0, greater than 0, be an arbitrarily small constant, depending on 1 over epsilon. We fix an integer h, and for j in between 0 and h plus 1, we can define the set mj for this monomial. Now, just before I carry on, this integer h is exactly the same like how we find it in the Coppersmith of univariate case. So since they are quite related, so that's why I prefer to use the Joachim May's strategy in my study in this case. But the only thing that becomes complicated is when defining this set of mj of monomials, because sometimes it could be confusing, especially when the monomials form, it's not in the set, but you have to include it for the further analysis. So this is the set of mj defined, okay, where L is the leading monomial of Fn with coefficient Al. So it is assumed that this monomial from f until f power h minus 1 are all contained in the monomials of f power h. So at first glance, reading this set notation might be confusing. So later on, I will also try to demonstrate using an example to catch your attention in a simpler way. And this set of m is especially useful when we want to construct the shift polynomial, that is the G polynomials. Now, the following defines the shift polynomial that has the similar strategy as in Coppersmith method. That is, when you look at the form also, you notice that there are similarities here, except that we have to choose carefully how we want to include the monomials or the variables in the Gx. Since now we have two variables of x, y, we must do the shift carefully so that it reduces the dimension, and at the same time, it makes our computation simpler and more efficient. So this monomial, okay, the highlighted one is the one that I would like to drag your attention for the later part. Now, if you find it reading this shift polynomial notation, it's confusing and you are not familiar with that, then using the example will be a better illustration, okay, for you, probably, hopefully. Now, suppose we want to consider a small example of the modular bivariate polynomial. So f of xy, which is 1 plus xy squared plus x2 squared. Now, in this case, we notice that the total polynomial, the total degree is 3, and there is no any condition where the variable x is greater than y or vice versa. So we follow the lexicographical order. We let x be the bigger variable. So x squared y will be the leading monomial in this case. So here I let h equals to 2, since in the earlier slide I mentioned that most of the time we can try to consider up to the f power 2. So for us to reduce the dimension of the basis construction and also for the efficient computation. So since we have let h equals to 2, expanding f squared, we have this expression. And notice that there are a total of 6 different monomials in the set. So we've collected all the monomials. So this is the set of the monomials. Now we want to build a lattice that having all the above monomials in the columns. So after having this set, next our target is to build this. So before building that, so I have for following the shift polynomial described by Joachim Mays. So I would also like to drag your attention to the red highlighted part here, because this will be our guideline in collecting and sorting the set of mj. Now with h equals to 2, so our j can take the value of 0, 1, and 2, and we can now firstly define the set of mj as follows. Now the definition of this set of mj so depends on this term. So if all the monomials can be divided by this term, leading monomial, then we can collect it in that particular set. So in this case, since j is 0, so this denominator becomes 1. So every monomial in the original set can be sorted and grouped in m0 set. So when j equals to 1, we have x2 squared, and the only monomials that is divisible by this x squared y is this 4 monomials. So we group that in the second set m1. And when j equals to 2, and the only monomial that is divisible by x squared y, the total bracket square, is this monomial. So the first thing that we do is to divide, group, and sort all this set of m accordingly. And then we can start to perform the next sorting. That is, we want to find what monomials is in the current set, but not in the subsequent set. So this is actually based on this highlighted part. So again, for the first step, after we group and sort, the next sorting is to find what monomial is in the current set, but not in the subsequent. So when we compare m0 and m1 between these two, so the only that is in m0 but not in m1 will be 1 and xy squared. Then we compare m1 and m2. So the only that is in m1 will be these 3. And so the remaining will be in the subsequent, the remaining set. So after further sorting out the set accordingly, so it's time to build the polynomial of Gx. So again, by referring to this formula, okay, so we have, this is actually from the first monomial, because one is actually x power naught, power 0, y power 0. So this construction gives us the first Gx, which is n squared. The second monomial gives us xy squared over n squared, and so on. So if we follow all the step by step, then we can basically construct different Gx polynomial. And notice that I have highlighted here the one seem abnormal constructed Gx, which is y cubed fn over n. So yfn multiplied to n. Okay. So notice that all the construction shift polynomial except the one that I've highlighted just now contain the monomials from the original set. And yes, indeed, if you look carefully, xy squared, these two monomials are also originally contained in the set, except y cubed. So if this kind of condition occurred, it will actually introduce even more new monomials in our basis later on, which we do not want it to happen, because that will definitely increase the dimension and next increase the computational cost. So as here stated in the third point, this will enlarge the dimension, okay, which contradicts to the aim of having low determinant matrix. So the solution, so instead of putting that abnormal monomial into the second set, we remain it in the first. So if we remain it in the first set, so the division of x squared y power 0 will return to this form, and notice that x squared y cubed power 4 is in the original monomial set. And by doing that and rearrange it accordingly, we can obtain the basis lattice B. So this approach, like I mentioned just now, is actually quite similar to the approach done by Coppersmith. So if we have the diagonal contain 0, then we basically just swap these two rows to make it non-zero. And having the upper triangular all zeros, so we can find the determinant easily, and also we can run the algorithm and find the resultant matrix that will reveal the roots. Now, in my self-study, I only stop until finding the basis, because finding the resultant matrix will be another study, which I am yet to go into deeply, but I will try to do it in the future. So if there's a next chance, then maybe I can try to share again in the future. And so my presentation is actually up to here, how to construct the basis, because having the basis, we can do many further actions in solving the modular polynomials. So for the bivariate modular polynomial cases, okay, it is frequently used in cryptanalyzing the RSA CRT scheme with known difference. That is, the difference of dp minus dq is known to the attacker. Also, it is frequently used in cryptanalyzing the common prime RSA crypto systems. So these are just some of the brief sharing session from my personal study. And yeah, this is the main reference that I use when preparing or studying the Coppersmith method for univariate case, because they provide a complete and detailed explanation of why this condition should be used and how the story goes. And yeah, this is in the chapter 19. And the ebook is available online for free. So if you're interested, you can take a copy. And I personally will recommend you to download the ebook version, because Galbraith often make corrections and modification in the ebook instead of the hard copy. So if you are interested, then you can get a copy of it and go through it. And for the case of Joachim Mays, I picked from the paper done by them. So a strategy in finding roots of multivariate polynomial with new applications in attacking RSA variant. So of course, there are some other Jutla and Nguyen Stern papers, which you can also refer to if you are interested. And yeah, that's it. I mean, for my sharing session. So if you have any comments or correction or any errors that you found in the slides, yeah, I appreciate if you can correct me on the spot so that I can learn from mistakes.